Welcome to today's session. So this is actually the fourth session, and we're going to do forensic analysis part one. So we're going to look at forensic analysis. So in the last session, you remember the last couple of sessions, we did the VQL fundamentals. So we look at VQL as a query language and looked at the syntax and how it actually works under the covers. But I mean, VQL in itself isn't that interesting without knowing how to implement forensic type or DFIR type use cases with it. That's really what it's for, right? So now we're going to use that syntax that we've learned from the last part, and we're going to actually learn a little bit in this module and the next module. We will learn about some of the forensic capabilities that are built into the tool so that we could use Velociraptor with those capabilities to build more advanced detections. Okay, so so just a quick overview of the module. We're going to look at some of the very basic forensic analysis and deep inspection capabilities. I tried to structure it so that this module looks at very basic level, at a basic type of analysis techniques, and then the next module becomes more specialized analysis technique. So in reality, though, most of the time you end up using the basic things like searching for files, searching for keywords, probably a lot more than the more specialized forensic analysis, like the SRAM, the prefetch, the SRAM, all of those more specialized parsing. I mean, they're good for what they do, but they're very specialized, and so you don't really use them that much. So it sort of happens that the more commonly used forensic techniques are actually the simplest ones. So we'll go over them today. So yeah, the same sort of thing. We can actually what we're going to do is we're going to work on the notebook to try and to look at how these capabilities are implemented in VQL, so that we could we can write artifacts. We've learned that last time, and hunt across the network. So let's have a look at the very first example. Just before, there is a question before we do that. Can I upload files to the client? Yep, absolutely. We're going to look at that in module 7, I think, as well. Yeah, it's module 7, how to upload files to the client. So that's great question. Okay, so let's look at the very first forensic kind of technique that we would use, and it's probably the most useful one: searching for files. So looking for file names. And this is kind of very, very common. You want to know whether a file exists on the endpoint, list all the executables in a certain directory, these kind of things. So in Velociraptor, we have this kind of workhorse for searching for files by name called a glob. And globs are actually they're supposed to be easy to use. So there's kind of like a wildcard. You have a wildcard, and you basically kind of search through the file system looking for star.exe, something like that, right? So it's just kind of like a wildcard search. It's a fairly common thing, and I think you have the same thing in the shell, or in the command shell or PowerShell or whatever, right? There are some differences though between Velociraptor's glob implementation and the shell. The first one is that the pass separators. With Velociraptor, you can use either / or /. It doesn't really matter on either platform. On either platform as well. So on Windows, you can use / or /, and on Linux, you can use the same. It doesn't really matter. Velociraptor supports both. We have star is the wildcard match, so that's pretty standard. You can also do these things called alternatives. So for example, you can say, star dot exe or DLL or sys. So show me all files with these extensions, DLL, exe or sys. This is also a very standard, it's a standard glob expression. But I think it's on Bash, it's standard. I don't know if it works on Windows like that, but on the Windows command shell. But it is a pretty standard thing. Remember that the globs are not supposed to be very sophisticated, so you can't really do a lot of complicated regular expression type matching with globs. They're only very simple, so they're supposed to be very simple. So that's about the extent of how complicated you can make it. Not very in the matching. But the main difference also with Velociraptor is that we have this concept of star star. And star has to kind of appear on its own path. So it's like slash star star slash like this, right? And what it does is it denotes a recursive search. So it actually says, okay, search the C user recursively all the way down and look for star.exe. So that's what star star does. I don't think the shell has star star. So this is kind of an extension of Velociraptor. So by default, I think it goes down 30 levels or something. So it goes down pretty much quite a long way. So it goes down a long way, right? So in many other tools, like in GRR, this is very expensive operation because it can actually go through and find a lot of files, because if it goes very deep, then it can actually collect a lot of files. It could be very nested. And so with GRR, I think it's very expensive, so they try and limit it so it doesn't go too deep in, because you never really know. The point is that you never really know, there could be one directory deep, or could be two, or could be 10. And you just don't know how many files you're actually going to hit this way. With Velociraptor, this isn't really a problem, because Velociraptor doesn't measure it can cancel with time, right? So it has a time limit, and it basically says by default search through 10 minutes, and then after 10 minutes it just cancels and immediately aborts, right? So it doesn't really. So if it's very deep, then it will time out in 10 minutes and it's fine, right? So it doesn't really need to limit the depth. So we don't really in Velociraptor really limit the depth that much. So here's the documentation page for the Globe plugin. And the interesting thing, can we upgrade this time limit? Yes, the time limit, of course, you can change, making it longer or shorter. Yeah. But I guess the point is that because other tools like GRR, they can't really cancel, so they can't really stop. So if they're about to do an operation, then it's unclear how long it's going to take. Like it could potentially be very expensive, like a globe. Then there's not really any way to to just go, oh no, stop. We've exceeded the time limit, or it's so you end up basically with a lot of impact on the endpoint. So they try and limit the depth. So try and take a guess, but it's difficult to know. But you have to kind of know how. I mean, you don't know what files are there, right? Is there a characters limit for the search for star? So there's a limit in the file system, right? Like you can't have a path that's longer than, I think, on Windows 32Ks, but I don't think there's a limit in Velociraptor on the path. Okay, cool. So this is the glob expression man page. So it tells you, like, you can use a number here to limit the depth as well if you wanted to. There's a couple of notes here that I just wanted to point out with globs. The first thing is that in Velociraptor, and this happens in the registry. We're going to see that you can globe through the registry as well, but we'll talk about that a bit later. You can actually sometimes have like slashes in the file name, and so that makes it difficult because you don't know whether the slash means a path separator or not. So Velociraptor uses this scheme where it will, if the path, it basically treats a path as a sequence of components, and then each component, if it has slashes in it, it gets little quotes around it. So this means that this is one big component, right? Even though it has slashes in the middle, that path is just like one path component, right? So in Windows, you can actually make directories with a forward slash. I don't know if you can make directories with a forward slash, but you can make registry keys with forward slashes in them. So like that. And so when you're globing through the registry, this becomes more important. So let's have a look at an example. I mean, these are the slides that are kind of boring. We'll just jump into the the practical. So as we're going to do that every day, we're just going to run the Velociraptor with the GUI commands, right? So Velociraptor GUI, and it's going to bring up the the same thing. We're going to open up a notebook. Let's create a new one. So this is going to be forensic analysis. Right. Submit. And I usually like to kind of open it up a little bit. Cool. So if we create a new cell, so let's have a look at an example. Select star from, it's going to be globe, right? Now, if I press question mark, then it will show me all the completions, possible completions, globes. So here I'm going to put C users *****.exe, for example, like that's the example. So I've got / here, but if, and let me just run that for you. Okay, actually, I should have limited it because it could take a little while because I don't know how deep it is. Yeah. So it works, right? If so, this is you can use // or if you're using backward slashes, like in Windows, because this is a string, right? Then you need to escape them like this, right? So you have to go double them up, right? Let me just show you that. So limit 5, because otherwise it's an escape character, right? So this is like a string thing, and it's very inconvenient because in Windows we happen to have a lot of backslashes, right, in a lot of things. So it's kind of inconvenient. So there is a way in Velociraptor to denote a raw string. So it's sort of like if you've ever used Python, there is a raw string in Python, which doesn't use backslashes to escape anything. And in that case, this is the raw string in Velociraptor. It's 3 single quotes in a row. And when you do that, then it's just a little bit easier. 3 single quotes, 1, 2, 3, is a raw string. And so it doesn't, then you don't have to escape, double escape the backslashes. Okay, we have one question. What about symlinked, hard-linked directories? Does VR avoid loops on those? Well, that's a very good question. So on Windows, I think we don't follow links at all, because this is actually a very difficult problem to solve symlink loops. On Linux, I think there is code there that detects symlinks, but it isn't that reliable. It's not that good. So sometimes there are problems. I think there is actually a bug on the issues page right now about this on Linux. Yeah, so probably this will become an option, I guess, in the next version. When we fix that bug, we'll probably have an option of whether you want to follow symlinks or not. There isn't really a good decision about it, because sometimes you do and sometimes you don't. And then some symlinks can cause loops. It does have loop detection, so we don't follow the loops. But sometimes there are some very complicated symlinks that do the unexpected things. Yeah, it is a problem. So for example, like if you do a recursive globe in /proc on Linux, then this is the current bug, right? Then what happens is in such proc, in slash proc, there is actually a link to slash to the top level directory. So suddenly, even though even if you avoid the loop, as in going back into proc, but you still end up searching the entire file system, right? Because there is a link that goes to slash. So it's that's not quite what is expected, right? So there is actually, yeah, it's not an easy solution, but it's a good question, excellent question. In some extent, maybe we can control it by looking at the depth or something like that. But on Windows, it's usually pretty good. You just kind of search recursively, and I think on Windows we don't follow the symlinks because there aren't really that many symlinks, and it's not that useful. But there are some, but not as many as on Linux. Okay, so this is just a quick word. Is it possible to search for ADS? Excellent question. Yes, it is. We're going to get to that in just a couple of slides. So yes. All right, so we'll go back to the slides. Let me just close that. All right, so this is basically how you do the glob, right? Now, when Velociraptor figures out the algorithm that it uses to glob through the file system, uses a common prefix algorithm. So basically, if you have a lot of globs to do, then it's much better to give the list of globs together at once, because Velociraptor will then figure out, like if you have these two, then it will figure out that it actually needs to walk over each directory and just automatically compare for these two names. So it walks over the files one time instead of if you did these globes, like two separate globes, is much more expensive than one globe with two expressions in it, right? Because it can optimize that out. So if you have multiple ones, you should use them like this. Yeah, of course. You can always use, in this particular example, you can use the the alternate syntax. You can use curly braces, dot curly braces, exe, comma DLL. Like we mentioned that in the last slide. Yes, but I'm just saying this is an example. I mean, it's not always that obvious, right? But like you might have a star here, and then you might have a subdirectory here that's already covered by the star anyway, right? But then it's still the same thing. It will still go through and do one pass over that directory instead of doing it twice, right? So it is still more efficient to, it's always more efficient to use one globe with multiple expressions. Another question, aside from using start.exe in the globe, is there a flag to determine whether a file is a PE? So this is a very good question. Globe just looks for file names. If you want to do other things, I mean, you're still doing a query, right? So you can do that with the query, right? You're going to get the list of files that match star.exe. And if you want to determine whether the file is really a PE or just has a .exe extension, then you can parse the PE, you can parse it and then figure out whether it is. So you can still, so the idea is that it's just a very basic building block, and then you can use that in your query to do other things, right? So this is kind of the approach in VQL. Cool, but these are all very excellent questions. Let me just go back to the example here, and let me just go and look at the raw data. As I mentioned last time, the binoculars show you the raw data, because I wanted to show you a little bit about how what data is actually coming back from this glob plugin. So you can see, remember that we talked about the result from Velociraptor is a row, list of rows, and each row is those curly braces. That's a row, right? So we have a name, there's a name column, there's a mod time column, there's a full path column, which is just a full path, relative to the C drive or whatever. And then we have these timestamps, the M time, which is actually the same as the mod time, so the same thing, B time, C time, and A time. So B time is the birth timestamp, and C time and A time, and it depends on the APIs. There actually might not even make any sense whether, you know, in this case, the M time is before the B time. We will see why that is actually, because it is possible to change the timestamp. So usually, like when, you know, when something is, you know, time stomped or moved back or unzipped, usually, then it goes back. Can you use glob in the registry? Yes, you can. We'll see that in just a second. But basically, and then we have the size and the dir, and is it a directory? So we need to know if it's a directory or not, or is it a link? So we can tell if it's a link or not. So that's the sort of information that we get from the glob. So the glob is really just used to search for file names in the directories. So excellent. Someone just asked, can we use glob in the registry? And so this is exactly the next slide. How deep can star go? Is it based on OS restriction, or can it go as deep as possible? So star go, star goes by default 30. You can increase it if you want. You just do a star and a number. And you know, and then you can go as deep as you can. There's no actual limit in Velociraptor, so it looks like, yeah, in Windows the maximum limit is 128. You say, okay, that's so yeah, there's no limit in Velociraptor. The default, if it's just star, then it's 30, right? Timestamps are from standard info entry, not from file name entry with NTFS. These are excellent questions. So yes, so the what you're seeing here depends on the accessor. So let me just hold your question for 1 minute and let me explain the accessors. These are really great questions because it looks like you guys are already thinking ahead. So this is awesome, right? So we've seen that glob is really useful because it's great for searching for files, right? You can write a glob expression. But then when you realize that there's actually a lot of different things that it would be cool to be able to search in that way. So files are the obvious thing, but you know, maybe we want to glob in the registry, you know, or maybe we want to glob inside like the NTFS. So we can use the NTFS parser to parse the NTFS in a low level, and then maybe we want to use a glob to actually hook into that parser so that we can search inside the parsed NTFS, you know, kind of virtual file system, right? And so these are examples of basically this. So we basically want to do the same thing, but just in different contexts. So this is the great idea of these called file system accessors. So accessors is like, you think of it as a driver. It's just a piece of code that provides an ability to access a specific type of thing that looks like a file system, right? So it makes it look like a file system. It's like a driver that makes it look like a file system. And so there's a whole bunch of different ones. These are only some of them, but there's a bunch of different ones. And using accessors, it allows us to take any plugin that expects to work on files and apply it in lots of different contexts. So for instance, and it's just a general concept in Velociraptor, right? So the glob is one example. You know, in here, if we have a glob, for example, so, you know, if I say, let's glob /star, right? If I don't specify an accessor, then it's going to tell me the top level of the file. So of the file accessor, right? It's going to use the file accessor. And the file accessor, the top level is the C drive. D drive is the drive names, right? Because Velociraptor paths really always start with a slash, the top level. So then we can say, you know, /C column / right? So that's the C drive, you know, and so on. The recycle bin and all that sort of stuff, right? So, what we can do is we can also specify an accessor. So that's when we specify an accessor, registry or reg, if you want to type that's the same thing. And then we can see when we run that, then the top level of the registry accessor is like HKey classes root. It's the top level is the hives, right? That's the top level. So now we can do things like slash, HKey user, this. Actually, it'd be limited to 5, but there's a few more hives. I think HKey users is another one. So that shows us all the users, right, with their seeds and so on, right? So it's like, so it makes the registry look like a file system, right? So you can glob into registry that way, right? Similarly, you can also use the Ntfs accessor. With Ntfs, it's just a different accessor, so it's like a different driver, I guess, kind of, and it presents a view that looks like a file system, and it uses the parser, the Ntfs, the built-in Ntfs parser to do that. So in this level, the top level is going to be the C drive, right? And if we do that, the next level is going to be the top level of the Ntfs, right? So you got the attribute, the back cluster, the Mft, and so on. I mean, we limited it to 5. We can increase that a bit, maybe 50, say. So the log file, the Mft, the mirrors. So it looks like a file system, right? But it uses the Ntfs. Now have a look at the full path, and you can see that the full path that the Ntfs driver gives us actually looks like // dot / C drive. So that the top level is actually a device name. And that's because the Ntfs driver parses the device, the raw device, the C drive, and then it builds the file system on top of that, the file system view on top of that. So the full path internally is always starts with the device name. And that becomes important later on when we look at VSS. So we're going to look at that. Another quick question: how are direct read possibilities of Velociraptor compared to CAPE? When using Velociraptor to pull triage artifacts using CAPE targets, can we access as much as we can using CAPE with direct read for logged files? So I'm not sure what you mean by direct read for log files, but the way it works is that when a file is locked in Velociraptor, so normally you can use the file accessor to access files, and it uses OS APIs like file open and stuff like this. But by default, the file accessor, if the file is locked, so it can't read the file, then it falls back to Ntfs parser. So then at that point, it just automatically falls into a raw Ntfs parser, and it accesses the file through the Ntfs parser transparently. So you won't even see that. So it still grabs the data from the disk, right? Yeah. So you won't actually even see that. So usually the recommendation is that usually use file for pretty much everything, because it means that file is faster, because you don't really have to parse the Ntfs for most files, because most files aren't locked. But then when you hit a locked file, it will just automatically use Ntfs, and you won't see that. It will just work. But if you want to get something that you can't get with the file APIs at all, like ADS, or like the special Ntfs files like $mft or $log file, things like that, then you can just use Ntfs accessor directly. You can just specify Ntfs accessor. So yeah, okay, cool. So yeah, the registry accessor is the example. It just uses the OS API. So the registry accessor uses OS APIs like registry open to just read keys and values. And it tries, what the accessors all try and do is make it look like a file system, right? So whatever they're doing may not actually be a file system at all. For example, we have a process accessor now, so we can read process memory like a file, right? But it's not really a file, right? It just makes it look like a file. in the process accessor, it probably doesn't make a lot of sense to glob for processes, but you can certainly do something like Yara scan a process, right? And that works, right? So you don't need to. So that's what the accessors do, right? They make it look like like a file system, but it doesn't have to be. So in here we use the OS API to make it look like a file system. So that means that we have an analog. It's like a of keys. The keys are like directories, right? So they make it look like a directory, and the values in the registry make it look like a file. So we can read the values, and then the key sort of looks like a directory, so we can glob it and stuff like that, right? So default values in the registry, like in a registry, keys can also have values in them. So there's no difference in the name. But we have to make a difference, so we call it at. So it's a pretty common convention to do that. But usually with the registry accessor, with registry, the value content is included in the data attribute, because usually values are very small anyway, and we can get them. So in that case, what we do is we put it in the data attribute. So let's go back to the registry again. So you'll see that every registry, I'll just go right, because it's just a little bit less to type. When you run, so you can put two queries and it just makes two tables, right? So it doesn't really matter. So the top table here, we're looking at the first 5 accesses, 5 keys, and then you can see that there is a data column. It doesn't have anything in it. If you look at, I don't know, we'll try and go in a little bit deeper. Oh, paste. Try and find some values there. I don't know, maybe environment have values in there. And you can use / or / the same sort of deal, right? Yeah, so you can see there's some values in here, right? So you can see that because we are already reading the values, from the registry, we may as well make them accessible somehow. So the value content is actually passed in this. So this data column is like a free-form dictionary of key value pairs that the accessor just tells us about this file, right? So all the other columns of the glob plugin are standard, and the data column depends on the accessor to what kind of information it gives you, right? So it basically says, oh, this is a type SZ and this is the value. So you don't necessarily have to open and read it. It just makes it a little bit easier for when you're globbing in the registry. Yeah, there's a question here. Okay, cool. The question is, while we're talking about quoting strings, could you mention quoting column names that contain spaces? Now, this is an excellent question that we probably should have covered in in the VQL part. But sometimes you can get column names that contain special characters like spaces or dots or something like that. And in that case, you might want to quote them. So for example, here we have full path. You can actually, it's the same in SQL. You use backticks like this, and then anything inside the backtick is the column name, right? So if you end up with a column name with a dot in it or space, then let me just show you how you would end up with something like that. You basically, for example, if you did something like, let's say you wanted to get the value here. So you'll go data.value. So you go select data.value, right? So that gives me the value, right? So this is the content of the key. Now, if I somehow let x equals, and then I wanted to select from it, and I wanted to get this column, right? So how can I do that? If I just do this, this is not going to work from X, right? This is not going to work because it thinks that what I want to do is I want to get a value called a column called data, and I want to access, and it's, access the value in it, right? So it has no idea what you're talking about. And in fact, it will tell me that it doesn't know what the data is, right? So it doesn't really work like that, because it thinks, if I just write it like this, it thinks that what I want is a column called data, and then I want to do a dot and then get value out of it. But I'm trying to tell it, no, the dot is really part of the name of this column, right? Because we selected it like this, right? So this is what you do. If you do that, then it's saying that column is, the whole thing is just the name. So that would work, right? So it's still inconvenient. So try not to get yourself into this situation. So, usually if you are in here, you can go as value like this, right? So that makes it a little bit easier. But sometimes you end up with these kind of situations. And so, especially if you're reading like a CSV file or whatever, so it might be a space. Yeah, space in the column name, the same thing, right? So sometimes you'll get a column name, like you're parsing a CSV file or something, and you'll have a space in there. Now, another question, does the registry accessor work against the registry hive file, or can it access in-memory hives like shim cache, not yet written to disk? Very excellent questions. So many good questions. So the registry accessor is just using the API, just the read-write API. There is another one called a raw registry accessor, which parses the raw registry hives. And the last part of your question is whether we can read the shim cache hive, which is not written to disk, which is in memory. Currently, no. So currently, we cannot extract it out of the memory. Does the registry accessor use the transactional log files? So the raw registry accessor, which parses the registry files, does not. The actual registry file, this one, it uses the API. So it would use the log files because it uses the API, right? Cool. These are all very good questions. Cool. Okay, let's go back to the slide. So this is the registry accessor. That's kind of all we want to say about that. We pointed out, that we can get the value, so that's great. And now it's time to do an exercise. Run once artifact. Okay, so this is a very simple example, but let's just work through an exercise of trying to find out whether we have run once keys. So let's go to the next slide and see what are those run once keys. Well, what are we talking about? So it turns out that there are certain keys in the registry that make Windows run software on startup or boot or whatever, right? So there's different kinds of situations. And this is where they are. There's a whole bunch of them. This is not an exhaustive list, right? But for this exercise, we're gonna look at this. And malware loves to put keys in there, right? So malware will put a key in there, so when the user logs in, then it will run. So what we want to do in this exercise is we want to basically try and find if there's anything in that in that hive. Now, I don't actually know if this VM has anything in that hive, but I guess we'll find out. So let's copy it. So let's start from here. Sorry, we'll start fresh, and let's look at star. Yep. So it's going to be H key current user, software Microsoft Windows current version run. Okay, great. So software what was it again? Software Microsoft Windows. Great. You know what? It's too much to worry about. We'll just do the start. Right. Okay, so this is going to give us all the run keys. I don't even know where they are, but whatever. And okay, cool. So what we're going to do is recursively search for it. So let's do that. It's not the most efficient search, but why not? So it's going to take a long time because I said, you know, recursively search through all the Hive. Oh, look, so we've got some, so that's cool. In the last course, I did it on a cloud VM, which was super clean, so there was actually nothing there. So that was kind of funny. So anyway, that's being lazy. So we found that there are some stuff in there, right? So some of them are like, there's a OneDrive, and then there is a binary thing here. You know, a startup approved. Okay, that's something else. But this is the one that okay, that we want to get to, right? So that's cool. So we found the run key. So what we want to actually do now is we want to actually convert that into some kind of a artifact, so you can actually hunt for it. So we want to kind of, I guess, productionize this. And what we want to, so we can find the key, all right, that's fine. But what we actually want to do now is we want to take a step back and think, how would I like to run this across the network to make it useful and actionable, right? So this is all about kind of trying to make the data useful. You know, so it's not just enough about just getting the key. What you want to do is format it in a useful way. And what I'd really like to do now is I'd like to run this across the network, and then I want to get the information about, first of all, what is the name of the startup program, you know, here. And, you know, for example, like OneDrive, yeah, that's kind of legitimate. Okay, fine. Then, you know, what would be also cool is to see when it was actually put in, right? So that's the M time here. But that M time is not for the value. It's actually coming from the key. Values don't have M time, only keys. But anyway, if I'd like to get that information, so it gives me a little bit more context of when it was possibly added. And then I actually want to get the time, the value, right? So most of these columns here, not super useful. The name is useful, the time, and, you know, and then maybe the value. So so I'm going to do the name. Okay, more time, so which is the same thing here. And it's going to be data dot value. And again, I usually startup path, right? So this actually interprets what does that mean, right? So now when I do this, then it basically will tell me, and then maybe tighten up this. So you see this, that was that binary thing that we, you know, it's probably a different, let's just also add the full path as well, because that gives me the path to the registry. So this is just the extra little step of making the thing more productionized. So, you know, then I can say, oh, you know, here's the proper place for it. So maybe copy and paste that instead of that star. So it's a little bit more accurate. It will also be faster. And I mean, either this or whatever. Yeah. So now it's going to be super fast because it's just going to get it from the right place, and that will also eliminate that other false positive. So that's cool. So that becomes more productionized. But there was a couple of other locations in here, right? So there was HK local machine run, HK current user run, and then there was the run once keys. So we can convert those, you know, maybe have a couple of them, a couple of globs here, right? You know, turn it into a list. Yeah, copy. This is what we've looked at before. Paste. Yeah. So that's kind of what we looked at before, right? So now we can go and say, you know, okay, HP current user, local machine, right? So it's going to be a software, Microsoft Windows, current version run. Yeah. And then the same thing, but run once, right? So So let's run. Yeah, so it gives us a few more hits, right? Use a star before software. Yeah, I guess you could do that. Yeah, to look at all the hives, because it's probably going to be relatively cheap. So you can do that. Yeah, use a star before hive, but maybe it's going to be expensive. I don't know. It's going to look through it in every hive. Maybe it's going to make more hits. I don't know. Yeah, so that's a possibility. But you see, now we've basically got a detection here, according to the okay, so that's cool. But let's take it up once. Why 3 single quotes? Okay, that's a great question. So we don't really need it in this case, but 3 single quotes are a raw string, right? So that means that we can use single backslashes. We don't have to escape them, because that's why we have the 3 single quotes. It's just that type of string that doesn't have, so you can put backslashes. We didn't really need to in this case because I used forward slashes, but you can use backslashes as well right here. Yeah, so actually that's true. We've got the backslashes here. So that's why we have the 3 single quotes. We don't need it in here in this case. But let's have a look at this example here. So here we have the program, right? Let's take it up one more step and say, well, no, actually, I've got the value of it, which is great, right? So this is the, a lot of tools will give you that, just reading a registry key and telling you the value. That's what that's what a lot of tools do, but that's not how we use Velociraptor, right? Let's take it one more step and figure out how, like, let's say the hash of these things. How do we actually go and say, well, first of all, is the file still there? And then what is the hash? Is it a good file or a bad file? We have no idea, right? And so you can see that we have a whole bunch of examples here of run once type keys. And what I would like to do also is have a hash here, right? But if I just went ahead and just said, okay, well, why don't we hash this startup class? So let's do it. Let x equals. We don't really need that limit there. And then what I want to do is hash takes a path, startup path, startup. Right? From x. So what it's going to do is it's going to try and hash this string, right? This startup path. This is the value, the content of the value. And if the value starts, if it looks like that, so that's fine, right? That's a file, and that's great. But it's not actually a file, right? It's a command line. So this is the whole command line. And if the command line doesn't, this doesn't take any arguments. So it works in this case. We go and we pick up the hash, and that's great, right? But in these cases, you see, it doesn't really work, because what is happening is it's trying to find, use the entire thing as a hash, right? And it's not. So what we need to do is say, well, actually, this is not a file name, right? This is a command line, and this first part is the actual file name, right? So what we want to do is maybe just figure out how to extract that file name in the query, so then the query can work with it, right? So we notice that there are a couple of different cases that we need to handle here, but let's handle them one at a time. So this first one, we can immediately find a rule to say, well, okay, I know what the file name looks like. The command that's going to run, it starts with a quote, and then there is something, a whole bunch of stuff, and then there's another quote, right? So let's try and extract that part. So what we really want to do here is we want to parse the string with a regex, right? So it's got a string, right? The data value is a string, and we're going to use a regular expression to just try and parse the value out, right? So let's see what parameters it takes. So first of all, it takes the string and then the regex. So let's give it the string data.value, right? And then the regex, let's figure out a regex that will extract it. So let's use single quotes because we're going to look at the rule. So it's going to be at the start of the line, there'll be a quote, and then a whole bunch of characters that are not quotes, one or more, and then a quote, right? So that's what we're going to extract. That's my regular expression. And so, and then I'm going to capture these things that are inside the quotes. That's going to be my capture variable. So in a regular expression, you have a capture variable, and that's what's going to be extracted from in this parse with string. So let's try that out. So so you can see that parse string with regex. So this function, it's a VQL function, right? So it's going to be evaluated. It's going to apply the regex on top of the string. So when the string has a quote, then it has a capture expression, which is G1. This is G means like a capture group, right? So you have capture group G1, G2, G3, G4. The more parentheses you put, right? So this is great. This works great, right? So this one, super. And in fact, that's what we're going to be hashing, right? So that looks great, but it doesn't work here because this one doesn't have a quote, right? But you can then say, well, okay, if it doesn't have a quote, then it looks like it starts at the beginning. So let's go back and find. So you can actually put multiple regular expressions here. So that's the first one we're going to try and match, right? But this expression here, it doesn't have a quote at the beginning. But so if it doesn't have a quote at the beginning, then it's going to go. We're going to start at the beginning, right? Start at the start of the line, and then until the space, right? So we're looking for a whole bunch of characters that are not space, right? And then a space. And then we actually want to grab the first example here, right? So that's going to be our second regular expression. Okay, so let's run that. So that's cool. Oh, wait a sec. Oops. So, but and also not quotes. Oops. Because if it had quotes, then it means that it would be the first example, right? So in this example, it's not space and not quotes. It's a bit better. Okay, cool. So this one worked because of the first example. This one worked as well. That looks pretty good. This one doesn't work. So let's add something there. Okay, we can put a potential space there that should get this example, right? So that's good. That one works. That one works. That one doesn't quite work because it has, well, it works in terms of extracting it. So that's good. So that's the next step. So let's say as binary or parse. Let's just go parse. So you see what we're doing is, so that just changes the name of the column to parse.g1. So .g1 is going to be the parsed one. So what we want to do is hash, when we're hashing, instead of hashing the startup path, we're going to hash parse.g1. Okay, because that's going to be the binary. So this almost works, except for this guy that doesn't quite work because it has a % expansion here. So the percent expansion it means that there's an environment variable that has to be expanded into it. So we have to take care of that, right? So we'll use expand the path using the environment. Cool. Question mark. It takes a path. Okay. So we'll expand it using the environment variable, and that should give us the full path name, right? So all the hashes work, right? So what we're doing is we're massaging the name into that, right? So then we don't need that. That's an intermediate one. We don't need it. So we can just simply specify the columns that we do need. So we want to get the hash. We want to get the startup path and then hash as hash. Okay, and then that should clean up the columns, right? So we don't care about the path ones, more in the intermediate one. So, right, so this is our example here, right? So that's kind of, that's a pretty cool example of when we run this query, not only do we get the keys, but we will actually can use that and go and grab the files from the disk or the hashes from the disk. So that is really important for enrichment. If you've ever done this kind of hunt, like, a lot of the time you think, oh, I'm going to do this hunt. I'm going to grab the registry key from the run once, and then I'm going to do stacking, and I'll figure out whether, everybody's got, OneDrive. That's probably fine. But then if there's some weird ones that, only one machine in my network has, then, then maybe I'll look into it. It's more suspicious. Well, that sounds like a good hunt, but if you've ever done something like that, you'd realize it doesn't work because the number of really unique run keys that you have in any real environment is stunning, right? It's absolutely staggering. It's just such a long tail, right? You'll have a whole bunch of very common run once keys that are used, like OneDrive is probably going to be on every machine, right? But then you just have this massive amount of tail of binaries of keys that are in the system that, are just very different. And it's not feasible to go and check each of them individually. So what you really want is a way of automatically enriching that and giving you a way to triage those things immediately, right? So for example, if you then grab the hash, you can figure out whether the file's even there still. A lot of the time the run keys are left over. The thing's been uninstalled or whatever, and the run key is still there. So it's not really relevant anymore. And then you can also get the hashes in VirusTotal or something like that, and you can get a really quick idea of whether it's malware or not. Because there's just a lot of junk. So this kind of thing really helps a lot. Okay, cool. So that was just an example of this VQL with the run once keys. There's a row registry puzzle. I think we might just go through it a little bit quicker because we're only on slide 13. Oh my God. So you can actually have the row registry parser. I'm just going to go through it really fast. It's the same thing as the Ntfs parser, but it's essentially a row registry parser. It's needed for, especially because so it looks at this end user. If you want to ever look at the end user dat file, it's locked, so it automatically uses the Ntfs parser to get it, right? So you don't need to worry about it too much, but it does that on behind the scenes. So it uses the Ntfs parser to gather the raw data, and then the raw registry data parser to access the keys and values. The only trick about it is that the name of the path of the globe that you're searching is built up out of a URL, and that's because the accessor itself needs to know how to open the actual file to parse. So it has to be, built on the URL. And the way it works is there is a scheme and there's a path. The scheme is like what accessor the underlying, accessor should use. And then there's a path and so on. But it ends up basically looking like this. So if you give this to the raw registry accessor, then this means to it, I'm going to use the file accessor to open this ntuser.dat, and then there's a hash, which means it's a fragment part of the URL, and then I'm going to look at this thing. It is a little bit confusing, but I'd say that's probably a more advanced use of that. So we'll just skip that. The URL notation is a little bit confusing, but from here, I guess all you can take from here is that you should use the URL function to build them. We'll skip that. The data accessor. Okay, so that is the data accessor is used to try and hide. As I mentioned before, accessors make something look like like a file system, right? But the thing that it looks like a file system may not actually be a file system. It may be something else, right? So here's an example of that. The data accessor is the perfect example of it. Let me just go up. Okay, create a new cell. So there's a whole bunch of files and go back. Whole bunch of VQL functions or plugins that use expect files. An example to that is the hash function. And if you push question mark, then it expects a path to open and an accessor to open it with. So if I had a file on disk, then it will go and open it and hash it, right? We've seen that before in the last example. But sometimes you want to hash a string like hello world, right? I want to hash that string. And if I just did this, then it would open a file called hello world and try and hash it, right? This is not what we want. What we want is to hash the string. So this is where the data accessor comes in. The data accessor makes the file name equal to a file. Like it creates an in-memory file that the content of it is that string. So when the plugin or function or VQL function tries to open that file with this accessor, then it gets an in-memory file, then it operates on it. So it's just a way for us. So we're just going to do scope, right? It's just a way for us to leverage all of the plugins and functions that use files, and then use them in lots of different contexts. Otherwise, think about what we would have to do. We would have to create a function that opens, a file like hash, and then we have to create another function that just hashes a string, because sometimes we need to hash a string, right? And it would be very confusing because we'll have lots of versions of the same thing, one operating on a string, one operating on files. So the accessor makes it unnecessary. We can always operate on a string, and you can always do things like Yara scan a string or parse a string or whatever, right? Just using this like data accessor. So I'm just going to mention that here. This is the example that we said, and we often use it to parse like things like CSV files that are in memory. It turns out that it's actually useful. This is how the CSV type of parameter is implemented. We can parse these the strings as a CSV, and it's a good way of basically introducing tabular data into your artifact as a parameter. So we'll just quickly skip that, but we'll see it a bit later on anyway, because I really wanted to get to the next part. Didn't want to run out of time. Okay, so that was globbing, right? So globbing is very cool. And then the next, so globbing is probably the most common DFIR tool technique that we use. The next most common one is searching data. And we basically forensics has always been about searching for keywords or searching for patterns of text or something like that. So, searching for credit card data, search for URLs, binaries, registry patterns, whatever. So probably it goes without saying that whenever we say search for something, we probably mean Yara, right? Because Yara is the most common tool and it's actually a really, really good tool for searching for, it's like a super powerful grep, right? Searching for patterns. So Yara is, if you guys aren't familiar with it, it's really optimized to scan for lots and lots of rules, so lots of keywords at the same time. So it is really fast, and we use it in Velociraptor. We just use the library, the Yara library. So we just kind of like use the library. We use the two things in the library, just Yara plugin, just scans a file, and then we use proc Yara that scans the process memory. So this used to be the only way to scan process memory, but now there is a process accessor, so you can just use the same plugin for both. So let's have a look at what a Yara rule looks like. It's got this kind of structure. It's a little bit verbose for sort of simple rules. So I mean, even a simple rule is kind of a little complicated to write, but it's designed to actually scan for lots and lots of strings. The way it works is you have a keyword rule, then the name of the rule, then you have this brace, then you have a strings section. And this is where you put all your strings. You give them names if you want. $A equals, you can have, this is a regular string, and then you can have a modifier here, no case, wide, or even a regular expression. So you put all of these in, and then you have the condition, and the condition says, what's it going to match? When is a match occur? The match occurs when A is matching and B or C or whatever, right? So you can play around with that, or you can just usually go any of them or all of them, right? Or whatever. Okay, so I've got an example here. It's kind of a little bit more complicated, but I like this example because it gives us a feel as to how we can use Yara in a kind of novel and cool way. And that's really the power of VQL, is to use things in a novel way. So let's just imagine that in this case, that there is a new browser on the market. Let's say Edge, right? But we have no idea what, where it stores its browser, where it stores its directories, its files. We don't know, and we actually don't even know what is the structure of the cache or the history files. Let's assume that, right? So it's basically very similar to a lot of cases in forensics where you come up against a new kind of software and you really don't know how it works. Maybe you can Google or something like that, but you don't know exactly how to parse these particular files. So what we want to do here is, so we have Edge. Do we have Edge on this machine? Yeah, we do have Edge here. So this is Microsoft Edge. I think that, yeah, that's the new one. So, there's a new Edge. Oh no, that's the old Edge. Okay. Oh, I don't want to download it. So I'll just use Chrome. Yeah, anyway, I think Chrome is probably fine. So wherever it says Edge, we'll use Chrome. So let's say we don't know how to parse the Chrome history, right? So the first thing that I'll do is I'm just going to do a little bit of investigation, right? Poking around. And what I want to do is I want to see, I have this Chrome browser running here, and I want to see a little bit about where does this Chrome browser write its files? Because it's probably where I'm going to look for. So the first thing I'm going to do is select star from PS list, right? So I'm going to try and see, investigate this browser on this machine. So let's see what kind of information it gives me. So I have the name, right? And this is just a normal process listing. Okay, great. So I'm only really interested in where name matches Chrome. Okay, so we've got a whole bunch of, oops, where name matches Chrome. So we've got a whole bunch of Chrome processes, right? And we don't know what exactly they do, right? But let's say we pick one, like this guy. So this process, I don't know, it's some process, but I don't know exactly what it's doing. So what I want to do is maybe I want to have a look at all of the open files that it has open, because probably some of these files are going to be where they store the cache, right? So in order to check out what open files, files are handles. So I'm just going to look at the handles. Okay, it takes a process ID. Okay, so for this example, I mean, we're going to do the for each later, but I'm just going to pick my process ID and let's limit it to, I don't know, 50 handles, because there's quite a lot of handles. So let's look at the handles. So there's all kinds of handles. This is the handles plugin, and it tells you all the handles in this process, and there's different types. So this, if you just kind of browse through them, you can see that there's like threads, there's keys. So this is all the registry keys it's got open, but then there's some files. Some of them are open. These are actually pipes. So let's at this case, we're just looking at where type matches file, right? So let's just look at files, and maybe we're going to look at all of them, right? So we have this one doesn't have too many files, but it's a Chrome process, right? So that's cool. So what we want to do is take this guy, and then for each of those Chrome processes, select star from for each. Okay, row equals. So for each of those processes, we're going to look at the file. So we just, is another example of for each. So for these pits, right? So for each of the Chrome processes, I'm going to list all of the files that it's got open, right? So let's see what that gives me. So I'm looking at the first 5, Chrome processes, and so I don't know what each process does, but I can tell you that it has some files open, right? And now this is kind of what we want for this exercise. So it just gives us an idea. We're getting some visibility about this Chrome thing. We don't know exactly what it does, but we can see that it's got files open in users mic, app data, Chrome, user data, default, and somewhere in there, right? So now we got more of an idea of where this Chrome thing works. So cool. So that gives us the directory where to look for. That's great. And now we are not really sure whether the user download. What we want to find out is whether the user downloaded from this browser, but we don't really know exactly how this browser is using storing the URLs. But probably it's going to store it in something that will look like a URL, right? So it's going to be like a database, but inside the database, there'll be URLs stored in the database somewhere. So let's write a Yara rule that detects something that, kind of looks a little bit like a URL. So let's have a look at that, right? So if we detect so this is going to be our rule, right? And we're going to apply this rule. So let's create another VQL cell, actually. Let's Yara rule equals. Now I'm going to use 3 quotes here. and paste this thing here. So in the latest version, in the next version, this syntax highlighting is going to be fixed a bit, but right now it's not highlighting correctly, but it still will work with this triple quotes. It's a raw string. Okay, so that's great. So that's one of the strings. And now we're going to look at, so we know select full path from, we're doing a glob, right? We're going to look for files that are in users, mic, app data, local Google Chrome user data defaults, right? So somewhere in there, this directory. So we're going to, let's edit that thing again. Yeah. And, C column, right? So again, we're going to use our 3 quotes here. That's going to be our raw quotes. Okay, cool. So let's just do a limit so there's not too many just in the first instance. Okay, so it's going to find, and we want to look recursively in there. So star, yeah. So it's giving us a whole bunch of files and directories. So, well, it's probably not going to, you can't store it in a directory. So let's just where not is there, right? So we can remove, if you recall from before, there was that is there field that told us whether it was a directory or not. So these should show us files. We can also see the size as well. Yeah, so that shows us some size. So now inside of these files, I don't know which, right? But there's going to be some URLs in this file. So what we want to do is we want to look at each of those files and then do a Yara scan of those to try and come up with the different hits, the different URLs. So let's do select star from. So for each of those equals, for each of those things, right? We're going to do a query. Select star from Yara. Yara is a plugin, and it takes a parameter, a whole bunch of parameters. So the first parameter is going to be, so there's a files that tells us the file to take, full path. So this path that it gives us here, that full path, that's what you should be opening. Great. What else does Yara take? So it takes a whole bunch of different ones, but I mean, the most important thing is the rule, like where to start, how many to hit. And so we're going to give it the rule. We're going to use this Yara rule as the rule, right? And then it has the number. So the number is like how many hits inside each file. And after one file, it stops, right? By default. So we're going to give it, lots. We don't want it to stop. We want it just to do all the URLs in the file, right? So that's gonna help us there. So what this is doing is, let's recap. It's going to look at all the files in this directory, and then for each of those, it's going to apply the Yara this Yara rule on it, and this Yara rule is going to hopefully match some of the URLs. Okay, so if we run it, then you can see immediately. Let's just stop quickly so it doesn't take too long. You can see that it's created a lot of hits, and you can see here's the URL. So it's making hits on URLs inside of these files, right? And over here we have the file name that hits, right? And then we have all kinds of information as well about it, like the modified time and stuff like this. But really all we care about here is the string. Now this is the data. The data is actually, it's not really hex encoded. It just looks that way because we are converting to JSON. It's really a binary string here. So we can actually convert it into a string. So from here, all we really want is string, which is this column here, dot data, so which is this one here, and we just want to convert it to a string, right? And that is the URL actually. Okay, and also we want the file name, and maybe also we want the offset, string dot offset. So let's put that in there, string dot offset, right? And let's have a look. Do that again. And stop. Yeah, let's see whether that gives us better. Yep. And where are we? So we've got all of the URLs, we've got the hits, and we've got the string offset in there. So if we have a question to say like, did the user download this malicious code from somewhere? Then we can already answer that. We can essentially run, yeah, so some of these files can't be scanned, so it just gives us warnings. But essentially, this is essentially a carver, right? So it goes through and carves all the files for URLs. Yeah, and we don't really, the idea here is that we don't really need to understand the data. We don't need to understand or parse any of these files. We just need to, so it's kind of like, we don't really have any context either, right? So you can see like, okay, someone opened this presentation here, but I don't even know whether, why they opened it, what does it even mean? When they open it, I don't have the timestamp. I don't know really anything about it. But for a triage, this is brilliant because usually you just need to know whether there was a hit at all, and then you can investigate in more detail. Yeah, good question. Is it possible to get contextual data with Yara matches like recall volatility in addition to the match itself? So what Yara is just a very simple match. So the only context, so you're asking about context is in before or after the hit? Is that what you're saying? Yeah, okay, cool. Yeah, I understand what you're saying. Okay, let me just show you. Yes, so basically, let me just, if we do a limit here, limit 50, then it will stop quickly. Yeah, so it gives us, so it's a little bit easier. So over here, you see that the hex data, so this hex data is exactly the same of this data, right? And it's exactly matches the URL. You can tell Yara to also include a bit of context around the hit. It's one of the options, right? So context is how many bytes to include around each hit. So for example, if I want to get like 10 bytes on the left and 10 bytes on the right, then it's going to give me a bit more context, right? So it tells me so that's actually really important in certain things, right? So yeah, I mean, in reality, I would actually also include context, but it doesn't really then match a proper URL. But that's okay, because what you can do is you can do the context and then apply the RSig again to the string to get the, without a context. So you can get both versions, context and no context, right? Yeah, exactly. Like searching for IP and you hit it in the IS log files, you're going, oh my God, that gives you context around where you're hitting it or whatever, right? So yeah, so you can include context around it if you wanted to. Yeah, but yeah, if you make a context 0, then it's, it looks a bit, more like a URL like this. Okay, cool. So we did that. Yeah, cool. So I just wanted to go through this exercise, even though it took kind of a long time, but just to try and understand what the process of doing this. And also because I love Yara and it's really cool. it's actually a really cool technique that you know, a lot of people underutilize. They don't really appreciate it, because if you think about it, you know, you can do both. If your rules are very loose, then you're going to get a lot of false positives with Yara, right? And it's not that useful. But if your signature is really specific, then it makes a really great signal. So the thing about Yara is to try and think of how am I going to get my signature to be really specific. And so when I run it against the whole fleet, then the results that come back are really high value. So I can, you know, go in and look at them in more detail. And yeah, the other thing is it is kind of expensive. So when you're actually scanning with Yara, you can actually also limit how fast it's going to scan. So reduce CPU load on the endpoints. And, you know, we've got client-side throttling. So I'll just show you that real quick. I think we mentioned it already. So when you schedule anything on the endpoint, oops, if you select a Yara, or anything really, it doesn't matter, but it's more useful with Yara. If I select the Yara scan and I go to specify resources, then I've got this ops per second. And that essentially in the Yara case, it means how many. So an op is just like an arbitrary operation kind of. And with Yara, an operation is defined as, like, I think as scanning 1 megabyte you know, per second. So if you go up per second and you lower that, then it will, you know, slow it down. It will scan slower, more slower. So you can do that. Okay, cool. So cool, let's move on. The next topic is uploading files. So, you know, we already mentioned with Velociraptor, we can upload files, and it's the VQL that causes that to happen. And really, it's very easy to do, right? All you do to upload a file is you just use this upload VQL function. So it's just a function, and when it evaluates, the file gets uploaded. So in the VQL, it's just really easy to use. So just to give you the next exercise, collect all the executable in the user's home directory. You know, you might want to say collect the executables in the user's home directory. So this is a very simple example of a query. Now we can do it in the you know, in this. Let's just create another VQL cell all the way to the bottom. Sorry, I'll create it from here. Okay, and let's go back to that query that we had where we looked at all the executable in the user's download directory. So globes equals users, and we're going to use all the users, right? Downloads star.exe, right? So that should give us all the users downloads. Right, so there's a whole bunch of these users downloads, so we can see them with the full path, right? But we actually in this exercise we want to actually upload them as well. So to upload something is very easy. It's like hashing, right? You just use the upload function, and it takes a parameter file. So we just give it the full path. That's the file, and that's really it. You can also specify a name. And then the name is the file name that you should store on the server. So which usually you don't need to specify because it's really the file. It's going to just use the file name from here. When you run it in the notebook here, then it will say uploader not configured. And the reason why is because there's nothing to upload it to, right? Like we're literally in the notebook. We can't upload it anywhere. So it doesn't make any sense to do that. So it basically, you see, it runs the query properly as normal, but it doesn't upload it anywhere because it doesn't know what to do here. And the reason is that the uploader does sort of the right thing depending on context. But let me show you how to actually. So the idea is that you develop the VQL up until the point where you wanted to upload it, and then you create an artifact, and then you collect it. So let's create a new artifact, and we're going to call it windows.upload user executable, whatever. So this is just the name. And again, these are all defaults, which are fine. You know, Windows like that. And we're just going to copy this guy over here. So it's a very simple query, but pretty much does the right thing. So now, just need to line that up. Now the question is, you know, maybe this is fine to be hard-coded, or maybe we want to add it as a parameter. So it makes more sense to add it as a parameter. So I would say, okay, generally you don't like the hard code stuff in here. So I would say, okay, upload globe. That's what it is, right? Globe. And then I just copy this guy, put it here, and we're just going to call it upload globe. Okay, so it's going to basically go through. It's just a standard globe, nothing special about it. And then we're just going to hit the full path and do the upload. We can give it a nicer column name, actually. That would be good. Yeah, so we'll save it. Okay, and now we're going to collect it from our endpoints. Oops. So there it is. Okay, so that's the one we created, the user executables. Now we have a parameter that we can configure, so we can change this globe if we wanted to in the UI. Otherwise, you know, we just go for it, right? And then you'll see that it basically it will just start to upload files, right? There we go. See, so but it's actually going to be quite massive, right? Because I don't know what it's uploading, all kinds of stuff there, right? So there is we might stop it. I don't know. Yeah, whatever. We can stop it. But you see, it basically went through and uploaded it, and you can start to see the files coming up here. Yeah, the .NET installer or whatever, right? So it could be huge, right? So obviously you wouldn't want to do that. But for this example, it's just an example, right? But yeah. Okay, cool. So uploading. We have not a lot of time for NTFS. So I'm not going to talk too much about NTFS because you guys probably all know about NTFS. So other than to say that, you know, the details of NTFS analysis are, you know, you can read a lot of books and stuff about it. But what I wanted to show you in this part of the workshop is how Velociraptor can use the NTFS parsers to get some very low-level kind of examples. So NTFS, I just assume you guys know NTFS, right? Just as a quick overview, NTFS is the file system on Windows, and there is a master file table, which is this big table in a file system that tells you all about the different files in the NTFS. So I have a picture of it, of the master file table. I have a picture of it here. So it's just a big table, right? It goes over there. So a table means a file that has records in it. So this is a record, this is a record, this is a record. All the records are the same size. So because they're the same size, it means that I can index or just jump into a particular record straight away, very quickly. So I don't need to, so each record has an ID, a Mft ID. And so I can just jump into each Mft ID. So each record represents a file on the disk. So, so that's Mft. It's a big table. the actual contents of the file is not stored in the table. It's just stored, on the disk, right? But the metadata about the file, so the timestamps and other things, are in this entry, Mft entries. Velociraptor has Ntfs support, which we can parse out. So we've seen, let's go back to this glob thing, actually. I've got it here. Let's get this out of the way. And if I added the Ntfs Accessor, and let's limit it to, I don't know, 5. So it's still doing the same thing, as any other glob, but you can see that we've got this. Let me just show you the raw data. So we've seen this before. We talked about the device being the full path starting with a device name. But the other thing is that you've seen that the data, remember we said that the data column just contains key value pairs that are relevant for the accessor. And when you use the Ntfs Accessor, it tells you the Mft ID of each column. So we can tell, which Mft ID it comes from. And then it tells you about the short name, long name and short name, these kind of things. Okay, and also there is a volume shadow copies. So volume shadow copies are a way of creating an additional, it's like a copy on write type thing. It's really cool. Let me create one really quickly. So on Windows, if you're in a server environment, you can use this VSS admin to create the shadow copy. But in Windows, I think this is an enterprise system, we have to use this WMIC thing. So let's do that. WMIC, shadow copy, call create volume equals. So that uses WMI to create a new volume shadow. And so I can actually use VSS admin list shadow. Oh, this is admin list shadows. Okay, that's better. So this lists all the shadow copies on the machine. So you can see it's something really interesting with the shadow copies is that there is the volume name, it's like this, global root, and then there's a hard disk volume shadow copy 1. Now with Velociraptor, it treats those, so this is actually a device name for the raw version of the shadow copy. So if you look at Velociraptor, and if you even look at the VSS, the VFS entry, the VFS view here, when I list the top level directory, then I will see, come on, is it doing it or not? Okay, if I list the top level directory, list directory, then it should show me the two different devices, right? So it should show me this is the VFS, the VSS, sorry, and this is the C drive. So these are the two different top level. Now, if we actually look at the properties of them, then you will see that this one is a shadow copy for C drive. That's the shadow copy, and this is the volume name, and so on. Like there's different, this different information about it, right? So that's the shadow copy. And what it is, it's actually a device, so we can use the Ntfs parser to just look inside of it, right? And it just looks like, it's just like a snapshot of the file system, at that time when the shadow copy was taken. So what this means is that you can actually do like a difference between that and and the C drive. So you can see which files have changed between the different times. So Velociraptor allows you to do that. There's a whole bunch of artifacts that do this kind of differences by themselves. Like, for example, like you can find all the VSS copies of the event logs by just doing a star here, and so it will find a C drive and then the one in the VSS. So this is like a simple way, but there are artifacts that do it properly that you can rely on. So particularly, if we just search for the VSS, then VSS, then you can see that you can give it a glob here, search files glob. So by default, like it uses the security event log, and then it gives you all the versions of this log. So if you want to collect that, collect that one, but this actually works on any glob, right? So you can give it, it's like a super version of the glob expression. So I can give it maybe all the secure, maybe start.evtx, for example, and it will do all the logs and give me all the versions of the logs, from the VSS or from C drive. And if the log hasn't changed, so it deduplicates it as well, right? So if the log hasn't changed, then it only sends one version, right? So I don't have to have multiple ones. It does take a little bit longer because it has to upload all the logs and upload all the VSS. So it's parsing both, but it's a good way to try and get evidence that may have been deleted if it sort of happens to be in the VSS. I'll just let that run for now. Just don't want to run out of time. The next, we have three different levels of parsing of Ntfs. The first level is just looking at the Mft, the master file table. And it uses this parse Mft plugin to scan the Mft file, the $Mft file. So, a lot of the time, what people do with forensic analysis is they copy the Mft from the there's a question here. Do we need to worry about input checking from the user? Input checking, you mean in the box, in the checkbox? Because no. Well, that's actually a very good. That's a good question, right? You might have heard of SQL injection, and you might wonder, is it possible to do VQL injection? Yes, it is. And that's why when we write our VQL, it's a very good question. I do want to cover that. So many things to cover. So if you look at your artifact, so this is an artifact, right? And you can see that you have a parameter, and the parameter, what actually happens here is the parameter is inserted into the environment. So then it depends what you're going to do with this parameter. If you're going to do things like string concatenation, or try and figure out like a command to run or something like this, then you can, in fact, open yourself up to SQL injection, command line injection, all the usual things. You still have that. But if you just pass that, so in here, when we're doing the search file glob, we just pass it straight into a glob expression, right? And so, we don't necessarily, we just parse it, and there isn't really an opportunity for injection here. So yeah, always be aware that it's possible to have command injection. Sometimes it's actually what you want. So for example, like, we have this command called shell, right? And this is actually the thing that's running, right? This particular one is the internal one that's running in the shell interface that I showed you before. And this artifact is actually totally designed for you to write arbitrary shell commands, right? Because that's kind of what it's for. So it is, see, this is an example. If you didn't intend for that to happen, then you would be worried about injection, right? But that's kind of what that is what you're supposed to do. This is what it's for. So because you don't want to allow any user to, because essentially, that's arbitrary shell command, then we can actually specify a required permission. And you say that you have to have this execve permission, which only admins have, to be able to actually use this artifact at all, because we are already saying this artifact gives you, by design, arbitrary command execution. So yeah, so in that case, injection, command line injection, that's going to happen, right? Because that's what we want. But it's a very good question that you have to worry about when you're writing an artifact. Okay, so real quick, let's look at the Mft. So the easiest thing to look at, let me just collect it first. That's the easiest thing. That VSS thing is finished. I just wanted to show you real quick. What have we got? Oh, so it basically told us all the different different files, but it didn't upload them. Oh, maybe I didn't. Did I? Maybe I needed to click an upload button. I'm not sure. Yeah, I think I did have no. Oh, it's just searches for it, but it doesn't upload it. I think there was another one that uploaded. Anyway, let me just grab the Mft. So just search for the Mft, and we have Windows Ntfs Mft. This one is very simple. It just basically grabs the Mft. So if you look at the artifact, it gets all the drives that are Ntfs, and then it basically uses the where is it? The Parsing Mft plugin to grab all the Mft things, and then you can filter them out, right, by the timestamps, like this time or that time, these kind of things. The example of event deleted. Yep, let's see if I have some time to do that. Let me just launch it. By default, it just grabs the entire Mft. It'll take a couple of minutes to do that. Can we show the example of an event deleted? Yeah, how do we do that? Let's delete some events. Event log. Yeah, so if I go to the event log and I don't know which one, like system event log, and if I wanted to clear the log, let's say, now I already have a VSS, right? So if I grab the event log from the VSS and then grab it from the, if I clear the log, right, and then grab the event log from the real log and then the clear log, I'll be able to get that. I just need to wait for Windows to get itself moving. Yep, and then clear. So we clear the log, right? And then in here, what we can do, there is event logs. Which one is it? Parsing returns event Windows event logs. And then we've got the search VSS, right? So if I select that one, and just to make it a little bit easier, we'll just do system.evtx. And then if I click this search VSS one, then it should find stuff, right? Because we've just cleared the logs, right? So it should find some things there as well, right? So that Mft thing is still going on. And this one, see, it found all the logs. And then when you look at the results, oops, then you can see, does it tell us where the log came from? Yeah. So you see, so this particular log event came from, you can tell that it's come from the VSS, right? Because it's cleared. But, so that's what it does. This particular artifact, it compares the two event logs, one from the VSS and one from, so this is the question can you show the example of events deleted that you can recover from the VSS? So anyway, while we were waiting for that MFT thing, we did that one. So yeah, that artifact does that VSS analysis. Okay, let me just go back here and take a look at that MFT. It's going to take a while, but I think results are already here, so we can just start looking at it. So this is what that artifact returns. It's just a big table of the MFT. So it really just looks at the first entry, second entry, 2, 3, 4, 5, and these are all just the MFT entries. And we get the MFT path, which is the full path. This is the path to the actual MFT. We get the full path of the file, inside of the file system, obviously, and then we get the file name. And then we get all these timestamps. So it turns out that NTFS has lots and lots of different timestamps in lots of different streams. What did I want to say about the MFT? Yeah, so it's actually really useful because essentially when you are using that MFT artifact, you're going to visit every single MFT entry on the file system. So if you want to do something like find, whether this file system had a particular file anywhere, does it have an tell me all the executables on this file system, then it's actually it's much more efficient to do an MFT scan than it is to do to do a glob, for example, because an MFT scan will look at the entire file system, and it's much more efficient. Where was I here? Does it parse for deleted files? So it just parses the MFT, and if the MFT entry says that it's not allocated, then it's deleted, right? So you can see in use is telling you whether it's allocated or not. So this is we can just jump over here somewhere. Oh, and we can maybe able to find some that are that are not allocated. Let me just show you what we normally do is when we collect the MFT. So this one is a full MFT scan, right? You can post process, jump to the notebook, and if you wanted to know some files that are not allocated, where not in use. Yeah, so in use is the column, it's true or false. We want to get the ones that are false, and we're just going to look at the first 50 that are unallocated, right? So I'm not sure how long it's going to take to find them, but it will just pull some out. Now what we can do, okay, let's go over here. What else did I want to show? Yeah, so when you where am I? 56. I've lost my place. Oh, there it is. Yeah, okay, cool. So if you wanted to look at where we're parsing all the MFT where the file name matches exe. So that looks at all the executables on the disk. Yeah, find all the executables on the drive that were created after Jan 20, 2020, right? So again, this one basically did a full scan, right? But I can click that. This one copies the collection, so it copies it and allows me to configure the parameters. So what I can do is I can put file regex, which is going to be $exe. That's a exe file that applies to the file name itself, and I'm going to say date after. What did it say? I don't even remember. Jan 20. Let's just do, like, I don't know, April 1st. I don't know, some date. And so when you do this, then it still does a full MFT scan, but it's only going to return the rows that match, so a lot less rows. So it should take a little bit less time, but more importantly, it's transferring less data from the endpoints as well. So you can do a hunt and you're getting less rows coming back, right? So it's much more targeted. I don't know how long it's going. How long did this take? This one took 108.91 seconds. So it's like 3 minutes. So we'll let that one go. It should be a similar time, but it will return a lot less rows. Okay. Mft entry, right? So an Mft entry can have multiple attributes and streams, right? And the previous example that we saw, it only shows high-level information about the Mft entry. So the Mft entry has, it actually took a lot less time because it's much more targeted and there's less columns, less rows. So so it's only showed us the stuff that's let me just segue here because it's really important. The traditional approach for doing MFT processing in digital forensics is let's just grab all the MFT files from all our endpoints, bring them all to the endpoint, and then run some tool on them to parse them. And then we're going to put some, put them in Excel or something, and try and start to, filter out those columns, those files that were created in the right times and build timelines and things like that. But so that's the traditional one, but that doesn't scale, right? Because if you have, any number of machines, like say 10,000 endpoints, the MFT itself is going to be like 300 or 400 megs. So pulling the MFT itself back just doesn't scale. Even if you parse it on the endpoint and just parse all the MFT on the endpoint and bring the results back, I mean, we're looking at about 300,000 rows per endpoint. And this is only a very clean machine. It's just been built, right? So on a real machine, you're talking about way more rows than that. And then all we're going to do is take all of this data and then start to filter it, and this does not scale. So it's much, much better to do all the filtering straight up on the endpoint. So when you are collecting the MFT, then restricting it, remember that here we restricted it by file names and timestamps. And we can do that, and it's much faster and it's much more efficient to do that. So you can think of it as the source of truth for the MFT is the endpoint. And so it's much better to do this filtering on the endpoint and just bring back those results that are relevant for your search than to bring back more data and then try and scale it up and process it. Okay, so this is just a bit of a segue there. Now, another cool thing about it is that in this kind of, when you collect all of these MFTs, what I always like to do is do a bit of a timeline, and you can do a timeline in the notebook here. So a timeline is basically what you are trying to do is show all the file names that are created sorted by time. So you can actually see this as a post-processing step. So for example, here, what we would do is we want to show like, let's say the full path, but what we want to do is put the time first. So you can pick any of the times. There's, as we mentioned before, there are many times, right? There's the created time or the last modified time. Now this created time, OX10, is coming from the standard information stream, and the created time OX30 is coming from the file name stream, right? So there's different ones. So we got all the 16 timestamps. There's a lot of them, but we can just pick one. So for example, maybe we can pick the created OX30. And then what I usually like to do is put that first. So it's just a little bit easier to see. And then I've got my full path and, maybe my size. I'll put the file size in here. Size. So that's this column. And I think the rest of them are not super relevant for a timeline. So if I do this, then it basically just, gives me, the whole, just these columns. But to make it a timeline, I want to so order by, right? Created. So I want to order it by that. That gives me a timeline, right? So it's basically going to run through and order everything, in order of time. So that builds me a timeline. Now this is much easier to do a timeline that's already narrowed down, right? So you see, we went through and we said, only give me the files that are after this particular time. So I've got a lot less files to sort. So this sorting is a little bit expensive, right? But what we can do is, if you look at the full Mft scan here, it's still the same. You'll still do the same thing, but but let me just copy this information from this hunt. Yeah, so this is a time. So it's still going to take a timeline. It's still going to take a long. It's going to take a long time. It'll still do it, but it will have all the events in it, and it will have 288,000 events just sorted, properly, and it will take a lot longer to do. So, but and then if you end up with essentially a timeline that you're just going to skip the first 90% of it, then what's the point, right? Okay, I'll leave that going while I'm talking about the next thing. Okay, we're a little bit over time, but talking about the timestamps, there are different timestamps in the different streams. We've got the standard information, which is that OX10 one. We've got the file name, which is the OX30 one, and we also have timestamps in the I30 stream. So there's lots of timestamps in NTFS. There's time stomping. I'm not going to talk too much about time stomping. There's an exercise here. You can play around with it. It's, I don't know if it's that useful. I know that people do the time stomping and it's possible to detect it, but there's just so much legitimate software that changes times on the system that, it's not really a smoking gun. If you see time stomped files, then it doesn't necessarily mean anything, right? Because it could have been unzipped. Like when you unzip something, it time stomps it. So we can play around it with the time stomping here and write some artifacts to detect it. But in practice, it's not. I don't think that's that useful. The timeline analysis, we've done that. We sorted it and we built a timeline. Timelines are useful because you can tell, when prefetch files and link files and so on are, see, so this one is like a full timeline. But in here, what you can do is we've built a timeline as before, and then you can create another cell from this cell. So you can see that this cell has, the timeline. So it's sorted and it's built. But now what we want to do is we want to actually look at filter that. So when we create a cell from this cell, what it does is if you can see that it's reading the results from the previous cell, right? So it's just reading what's in there, literally. So it makes it a lot easier to kind of post-process the output in another stage of this. So for instance, in here, I can say, full path matches, like, let's say, the prefetch files. Then I can see when was, when the prefetch files were created. I restricted it by executables. So I don't have prefetch files here. Maybe I should do it on the full thing. So create cell from this cell. Yeah, where full path matches.pf. Right, so so that's going to show me all the prefetch files, and it's essentially processing. It's post-processing the output of the previous, processed table. So so it's much faster. So we can narrow it down, and keep working. Yeah, so this gives us a little bit more context. Okay, cool. We have a whole bunch of skipped slides. So I've actually skipped slides here that, you guys can read if you want, but, we don't have time to cover. Okay, I think we are a little bit over time. Do you guys mind to go another 5 minutes? Because this is probably the coolest thing. Otherwise, we can do that next week. I don't mind. We can go another 5 minutes. Okay, cool. So the USN Journal. The USN Journal is like one of the coolest things that I think in Windows. And what happens here? What the USN is essentially, it's not the same as the actual journal that's used, in the journaling file system that's Ntfs. What it does is it actually writes records of whenever a file has changed. And the reason that it's created is so that backup programs can essentially understand which files got changed, so they can go and back them up, right? So there is a reason for it that's not forensics, but it turns out that it's such an excellent forensic source that it's really cool. So it's a file that's in the Ntfs file system. So it's a dollar file, so you can't really see it in the file system, and you can actually navigate to it from the VFS. So if you have a look at the top level of a C drive in Ntfs, using the Ntfs Accessor, then we can see those kind of Ntfs files, which are the dollar files. You can't see them in the file accessor. And then you will see this user journal colon $J. So the colon $J actually means that it's an alternate data stream. It's an ADS, but Velociraptor doesn't really care about ADS because it just creates a name that uses these colons. So it just looks like a separate file. Now, if you have a look at the file size, you see that it's absolutely massive, right? So it's like, in this case, it's 430 megs because it's a pretty new VM. I mean, it's just a new VM, but on a server, this could be gigabytes or even terabytes big. And this is the USN Journal. If I try and collect it from the client, then you'll see that it looks like it's 400 megs, and it could be quite large. But in actual fact, you see it stopped after getting 30 megs. So what is going on here? So it's telling us that it's sparse. And what does that mean? It means that it's a sparse file, that the file doesn't contain all the data. Let's have a look at the artifact that we've just collected. Remember that the GUI just collects the VFS artifact. And look at the Uploads Files tab. And over here, you can see that this is the file size. File size is 400 megs, but the upload size is only 41 megabytes, right? So it's only uploaded 41 megabytes. And the reason why is because this file is sparse. So let's have a look at this file. So the file size is quite large because every new records are being written on the end of this file. They're just getting appended to the end, right? But then Windows reclaims the front of the file by making it sparse. So this is where it's kind of like consuming these every now and again. It just kind of like it doesn't delete the file, but it deletes those blocks in the file by just extending that sparse part of the file. So it's like, so the end part is actually real, but the beginning doesn't exist, right? It's just a big hole in the file. So this is important to understand. So usually there's about 30 or 40 megs here in practice, right? And that's really cool. Let's have a look at what actually is in the journal. And the best way I can show you is just to collect the journal, right? So I'm going to go USN and just grab the USN. So it just parses it, right? It just uses the parse USN function plugin, and then I can also filter it. But let's just grab the whole thing. It doesn't take too long, and there's not that much data in it. There's about 40 megs, right? So we're going to have, I don't know, a few 100,000 rows, and then we'll be able to see what we've got some rows, so we can look at it already. And this is the type of information that you'll find in it. So the first thing is the USN number. So that's the ID of each record. then you have a timestamp of when the record was written, then you have the file name, and there's actually an MFT entry in there, and Velociraptor will take that MFT entry and try and resolve it to an actual file. Be aware that if the file is deleted, if that file was deleted, then this resolution may not work or may just give you just junk, right? So it's not foolproof, but it's pretty good, right? So just be aware this full path here is not always correct, right? But basically what happens is it's recording, when what changes were made to this file. So in this case, this file was extended, it was created at this time, and so on. And here was deleted. And if we look further down, we can see some deletions. You see that file was deleted at that time. So you can see both when the file was created and when the file was deleted. And this is really cool because remember that it actually doesn't really, this journal doesn't rely on us looking at unallocated MFT entry. It's just a journal. It's literally something that's written down that says, this file was created here and was deleted here, was created here, was deleted here. And this data is invaluable because it's really, really great. When you're doing a forensic and you're like, what happened on this system at this time? If you happen to be there quickly enough to grab that USN log, then you know exactly what happened on that file system in this time, right? Because even if a file was deleted, you still know that it was there and it was created, when it was created, when it was deleted. And this is really awesome. Also, the other cool thing about it is that you can tell exactly when the file was modified. So let me show you another really cool example of the USN. We're going to talk about this in the next module about the prefetch. But for prefetch files, we actually, what happens is when you run a binary, it updates the prefetch file, right? But prefetch files only store the last 8 times that they've been modified, right? So if a program runs a lot, then it's only going to remember the last 8 times in the prefetch file itself, right? But if we look at the Usn Journal, then we will see every time that prefetch file was being modified, we will see that it was modified. Like this particular guy here, it was modified, here and so on, right? So every time it was being modified, so actually each change may take several operations, but it actually, it goes as far back as that Usn Journal. So we actually can tell sometimes a lot more than those 8 timestamps. So it's very cool. Usn Journal is very cool. Now, the most critical thing about Usn is that you need to grab it as soon as possible because it gets cleaned out. So it depends on sometimes you can't get to the response part for a while after the event happened, and as soon as you get there, capture the Usn, or at least parse it out, the Usn Journal like I just did, so that you capture that evidence, because it's only about 30 or 40 megs and it gets overwritten. Sometimes if the system is not very active, then it will last a week or 2. But sometimes if the system is active, very active, then it only lasts a day. So you've got to. So it's actually pretty cool. All right, so that's the Usn Journal. I think that is the coolest thing. What do we have here? Oh, yeah, so we can actually filter it and find things like link files when the link files appear, and build up user activity based on that. Okay, so post process with. Okay, so that's the Usn Journal. All right, so we kind of rushed through this module. There's a lot of material in here, but this module covered the basic forensic capabilities in Velociraptor, and you can already see that we can do so much with these basic building blocks of globing, of searching, and of Ntfs analysis and its various, various artifacts from Ntfs. So, but the best use of VQL is to put together those building blocks in a new, novel way, and be able to then use those things to develop, some pretty cool detections, and think out of the box. Just like we applied the Yara signature to just come up with URLs, we'll think out of the box and try and come up with new kinds of ideas. Okay, cool. So so that's that. Volume shadows, we also cover volume shadows. Next time, what we're going to do for the second part of the forensic analysis is we're going to look at more sophisticated and more specific types of parsers that are in Velociraptor for different kinds of evidence. And I mean, I think a lot of them are pretty easy to use. So we're going to essentially skip a lot of, so there's a lot of skip slides here we can look at, but we're going to really look at event logs and things like that in the next one. So it'll be more of, more kinds of forensic capability. Cool. All right. And as always, if you guys have any questions, let me know. Send send me an email or jump on Discord. Have a play. And thanks for attending. Stop the recording.